Hello everyone, this is Dr. Abdul Pasha. So, we are in the course of Power System Operation and Control. So, this will describes today's class about automatic generation and control. Simply we termed it as AGC. So, this will describes the control action in power system network. So, what is automatic generation control or AGC concept? So, automatic generation control is a continuous process. So, what it will best describes means that keeps the power system running smoothly. So, and effective operation will be expected from this AGC concepts. So, this will be done by making some auxiliaries. So, those are balancing generation and load. What is balancing generation and load means? Whatever the amount of power required to meet the load demand or load requirement, we need to make the power to be generated. So we should make over the power generation that should be in balanced nature. So here our automatic generation control concept will balances the amount of power that should be generated with the amount of power being utilized. That balance is achieved by this control action called automatic generation control. Second parameter is about controlling frequency and voltage. So here AGC will keep the frequency and voltage of the power generation stations within the prescribed limits. It maintains the suitable ranges and it will keep the frequency voltage under nominal cases and maintains the suitability. By that it can be suitable to make the controlling the frequency and the voltage case. By that the power system can ready to keep the frequency and the voltage to the desired expected level to meet the load demand. One more parameter in AGC is regulating power flow. So even though the power is generated, there should be some regulation of the power flow. So here our AGC, automatic generating control action, will regulate the flow of power in between the different areas of an interconnected power system network. So here AGC will faces several challenges. So what are those challenges means? Meeting the variable load demand and also renewable generation case. So what happens with the variable load demand means the demand power can vary, which can make it difficult for AGC operation. So here coming to renewable generation operation, amount of power generated from the renewable sources like wind, solar, whatever it may be, they can ready to vary, which can make it difficult for AGC to operate. So these are the aspects we'll cover for making the AGC to be suitable. And one more parameter is communication. So here AGC will require to coordinate multiple systems. There should be a communication in between these systems, one system with each other. Then this communication will helps to improve the efficiency of the system. So here it requires communicational aspect considerations and cooperation between the control centers and the local controllers. When there is a coordination between in such a controller or a coordination in between the controllers case, then there should be the AGC case. And maintaining the cyber security. So here AGC will need to be protected. We need to make the protection from cyber threats, and the communication network needs to be reliable. If not, the communication system is supposed to be in such a manner to make the system in operational aspect, then it will malfunctions. Their protection may loses and the result may be changes. Next case is the spinning reserves. What happens with the spinning reserves means So AGC only effective when there are enough spinning reserves. It will ready to operate perfectly means it should occupy enough spinning reserve. The spinning reserves are depleted. What happens? Means AGC is not ready to maintain the system frequency. So that's why your spinning reserves should be enough more. According to that only AGC can give the suitable results. So here the main purpose served by this automatic generation control is to use to maintain the acceptable frequencies. It should be during normal operation due to the fluctuations cases, in load and variable resources cases. And as an early response to the system contingencies like unexpected loss of a generator, or it may be due to the transmission. So these are the parameters which may expected from the AGC. So these units are used to provide frequency response reserves, which maintains the system frequency to be constant, and it should be in such an under control to make the system work, right? So according to that only the AGC can ready to operate. So basically the IEEE is ready to define the automatic generation control. By that, as the regulation of the power output of the electric generators are within the suitable area or prescribed limits in response to changes in system frequency. So what happens with this means the tie line loading or the regulation of these to each other so as to maintain the scheduled system frequency. As it is ready to maintain the scheduled system frequency means it can ready to accept the limits. So automated controls can manage repetitive and time consuming tasks. They may result in increased production rates. So and also it can ready for improved turnaround times and decreased operational costs. So human errors are inherent. They are one part of the manual processes. So like that automatic controls can manage repetitive actions which can ready to make the time in a variable case, and they may result to the rates of the production levels which is ready to turn around the various time aspects, and they can make the decrease in operational costs. And because of the expectancy of the human errors, involvement of human errors, one of the parts of the manual processes system can may malfunctions. This may be expected from AGC. What is the working principle of automatic generation control means here? If the input variations are reflecting on the output signals, then in a non-linear manner, they belonging to a non-linear closed loop system. So they can regardless of the input-output relationship, and here AGC helps to maintain the desired constant output for a given particular system, and because of that only the response reached from the AGC can maintain the system to be suitable. And coming to the classification of AGC technologies, AGC can be divided into RF analog control and ADC front-end digital control. This can maintain the AGC to be suitable. So here the earlier works by extracting the analog signal received by the receiver as the control parameter. That means while the later extracts the digital signal at the back end of the ADC as the control parameter is involved. That means AGC can ready to control the frequency and active power flows, which is most important in the power system network, as we already discussed in the frequency aspect. That means the system AVR maintains the voltage profile, that is automatic voltage regulator, which can ready to change the or regulate the voltage levels to the extended case. That means which maintains the voltage profile and reactive power flow in the power system. Because of that only you can maintain the suitable power factor operating ranges. Here, the main objective of the power system operation served and control is to maintain the continuity of the power supply. This can be suitably achieved by maintaining the quality of the power system. This can be within the acceptable limits or quality. This should be reaching to all the consumers in the system. So as the system is in equilibrium condition, when there is a balance between power demand and power generated, so as the power in the AC form has real and reactive components. That means the real power balance as well as the reactive power balance is ready to achieve. So this can making the balance means the automatic generation control action can ready to reach the system levels. So basically there are two control mechanisms that should be used to achieve the reactive power balance, that is acceptable voltage profile and a real power balance with acceptable frequency values. So here the earlier is called as the automatic voltage regulator that we already discussed to make the or to regulate the voltage to the suitable extents, and the later is called the automatic load frequency control or automatic generation control. This can ready to accept the levels of the power system network. Next consideration is generator voltage control system. That means the voltage of the generator is in proportional to the speed and excitation. Means by varying the flux to the generator, it can ready to make the voltage to be in proportional to the speed. That means voltage of the generator is in proportional to the speed and also flux, and it will be also associated with flux parameter. One is speed and another one is flux. Here n is speed, the phi is the flux. This is considered in RPMs and this will be in Webers. So this maintains the excitation of the system. So the speed being constant, so excitation is used to control the voltage. So therefore voltage control system is also called as excitation control system or automatic voltage regulator. So this can make the regulation of the voltage suitably. So for the alternators, the excitation is provided by a device or a machine or a static device that is to be called as exciter. So for a large alternator, the exciter may be required to supply a field current about as large as 6.5 kiloamps. That should be happens at 500 volts, and hence the exciter is fairly large machine. So depending on the way the DC supply is given to the field winding of the alternator, so which is connected onto the rotor. So exciters are supposed to be considered in various aspects. That is one with the DC exciter, another one with AC exciter. So these are the DC and AC exciters case. And one more exciter existing in the system is called static exciter. So accordingly, several standard blocks are existing. Those are implemented by IEEE working group to represent the excitation systems. The IEEE developed one of the latest blocks which can represent the one of the groups of the excitation systems. So that arrangement is shown as the schematic model for excitation control. So what it contains means this is the control block. This control block is initially connected or excited by reference voltage, and here it is operating with a certain frequency of voltage Vf. This block is connected to one of the amplifier extended block. This is called extended block. This extended block is connecting to the amplifier circuit, which will smoothens the input case, and this exciter is connected to one of the armature set, and this armature set is containing one of the field winding. Here this is called field winding with a number of turns, and here the response of the voltage is in terms of EF. So this path is connected as feedback to the control block for making the stabilization process. So that entire system here connecting means the blocks are connected by one of the generators. This is the generator block, and this generator block is supposed to be connecting to the rectifier section. This rectifier section is further ready to nullifies the distortions produced in the system, and this is connecting again as feedback path to the input action. Thereby, any one of the distortions existing in the system should be filtered here by this rectifier system, and that should be given as one of the feedback path to as input to the one of the control block. So this will maintains the system parameters suitably. So here one of the simplified block diagram of the generator voltage control system is represented as the generator terminal voltage is compared with the reference voltage as V reference. This is ready to obtain a voltage error signal as delta V case. So this signal is applying to the voltage regulator as we already discussed in the block with the transfer function as Ka by 1 plus TAS. So output of the regulator is then applied to the exciter as shown with the block of the transfer function as Ke by 1 plus TES. This is nothing but output of the regulator that is applied to the exciter with the block of the transfer function. That block of the transfer function is Ke by 1 plus TES. So the output of the exciter is given to the field winding, so which will ready to adjust the generator terminal voltage. So the generator field can also be represented here. That should be done by one of the block with the transfer function as Kf by 1 plus STF. So total transfer function here will be considered as delta V by delta V reference. That means G of S by 1 plus G of S is considered for this reference voltage, where G of S is Ka, Ke, Kf by one of the transfer function constants 1 plus STA, 1 plus STE, 1 plus STF. So these ratios are one of the regulating voltage constants as delta V by delta V reference. So which is maintaining the frequency of the functionality will be constant. So here stabilizing compensator is shown in this diagram. So this is ready to improve the dynamic response of the exciter system. That means input to this block is the exciter voltage and output is a stabilizing feedback signal. That means this is ready to reduce the excessive overshoot. When there is an excessive overshoot in the system, that excessive overshoot can be nullified or removed by this one of the block of the exciter voltage, and this will be treated as stabilizing feedback signal. This is ready to maintain the excessive overshoot of the system. So here delta V reference is considered. These all are the control blocks, and this is the amplifier section, can be treated as Ka by 1 plus STA, and this control block is connecting here, and that may be connected to the exciter section as Ke by 1 plus STE, and the generator field is connected as Kf by 1 plus STF, and that change is taken as a feedback path to the exciter stabilization case, and the delta V case is taken as one of the feedback to the reference section, and this will ready to excite the system voltage. The response that should be expected from this system is ready to amplify the case and which can make smooth over for the system case. This is nothing but simplified block diagram of the voltage section of the control blocks. So what is the performance of this automatic voltage regulator loop? Means here the purpose of the automatic voltage regulator loop is to maintain the generator terminal voltage, which should be taken in acceptable limits. So a static accuracy limit in percentage is considered for the AVR, so that its terminal voltage is maintained within that value. And if you consider it as one of the example, then accuracy limit is about 4%. Then terminal voltage will be maintained within 4% of the base voltage case. So due to which what happens means the accuracy limit will goes to high and terminal voltage is maintaining constant. That means this should be treated with a value of 4% of the base voltage. So here performance of the AVR loop is ready to measured by ability to regulate the terminal voltage. of the generator within the prescribed static accuracy limits. So with that acceptable speed of the response, suppose the static accuracy limit is denoted by AC in percentage with reference to the nominal value, then what happens to the error voltage means error voltage to be less. That means which may consider to a value of AC A suffix C by 100 as the product case of delta V reference. This change of referral may take in place at which it is ready to occupy the system conditions. So this can make over the system parameters to be suitably. So from the block diagram aspects, for a steady state error voltage delta E, then we may see that delta reference voltage minus delta terminal voltage that should be less than AC by 100, and delta E becomes delta V reference minus delta VT, which is equals to delta V reference minus G of S by 1 plus G of S as the product of delta V reference value. So when it is treated with 1 minus G of S by 1 plus G of S, as it is the product of delta reference value. So for constant input condition, when S tends to 0, then delta E is 1 minus G of S by 1 plus G of S. That means this will be one of the referral section that will be treated with 1 minus G of 0 by 1 plus G of 0 as delta V reference is going to be considered. So when it is equating to 1 by 1 plus G of 0 with the delta V reference, that means which is equals to 1 by 1 plus K as one of the delta reference voltage case. So here K equals to G of 0, which is treated as open loop gain of the automatic voltage regulator. So that what happens means 1 by 1 plus K as a delta V reference, that should be less than AC by 100 as a delta V reference case. So it should be traveling in between these cases. That means the delta value is treating in between AC by 100 case. That range may be existing or it may be treated as K greater than 100 by AC minus 1. So this is the open loop gain of the automatic voltage regulator. So here is an example considered, that is based on that AGC concepts, we need to calculate the open loop gain of the automatic voltage regulator loop. So if the static accuracy requirement is 3%, then we need to make it as AC as a 3%, that is static accuracy. So when K greater than under 100 minus 1 case, then K greater than will be equivalent to the value of 32.33. So what happens with this numerals means, if the open loop gain of the automatic voltage regulator loop is greater than this value 32.33, then whatever the terminal voltage will be within the 3% of the base voltage, Yes. So here automatic load frequency control is coming to the action. So that is ALFC. So this automatic load frequency control is to control the frequency deviation. That is by maintaining the real power balance in the system. So here the main functions of the automatic load frequency control are to maintain the steady frequency and to control the tie line flows and distribute the load among the participating generating units. So that means control of the input signal, those are the tie line deviations as a delta P tie line, which is treated under measured from the tie line flows, and the frequency deviation delta F, that should be obtained by measuring the angular deviation cases. This angular deviations make the automatic load frequency control to be maintaining the constant. So the error signals delta F and delta P tie line are amplified, mixed and transformed to a real power signal. So because of that, which will controls the value position. So depending upon the value position, the turbine, that means input section as of the prime mover, changes its output power. That should be to establish the real power balance condition. That means the complete control is expressed here. Here steam as one of the water condition, as it is given to valve or gate case. This valve or gate is connecting to the turbine mechanism. So this turbine mechanism is treated as one of the section T, and this is connected by the generator system. So this generator will produce the voltage as to the power network, and this generator speed can be controlled by governor mechanism with omega speed, where omega is one of the speed consideration. This can be given as one of the feedback path to the valve mechanism. So the entire blocks coordinated here as one of the control actions will ready to treat the system response. That is making the control system to be complete path. So which makes the system to be smoother under various conditions. So when the load on the system is composite and containing frequency independent component and a frequency dependent component, so load can be written as delta PE, that is delta P naught plus delta PF. Here delta PE is the change in the load. That means delta P naught is the frequency independent, that is treating as one of the load component. Here delta PF is the frequency dependent load component. What happens with this means delta PF becomes d delta omega, where d is called the frequency characteristics of the load expressed in percentile change in load for 1% change in frequency case. So because of these variations or changes, the AGC can ready to absorb the system conditions. That means only 1% of change in frequency will make the entire Thailand system conditions. So as the characteristics of the load are expressed in percentile manner, then they will make the frequency independent of the load component case. So when frequency dependent component is considered, the load on the system is making as composite case. So due to which the response of the system cannot be treated to be as a singular case. That means these systems may suppose it to vary with respect to the change in variables case. When D is about 1.5%, then we may expect 1% of change in the frequency causes 1.5% of the change in the load case. So the combined generator and load, they may constitute to the power system. That means they can be represented as delta P naught of S, delta PM of S as one of the control variables, and this system is connecting to 1 by 2 HS, as it is given as feedback path as a D section, and delta PM of S to the delta P naught of S is considered. This may treat as one of the input section for the given first block of the system, as it is reaching to the delta omega of S case, and this block may extended with 1 by 2 HS plus D case. That means here we may expect it to see delta of omega of S, due to which the response of the system may be changed with small value, even though that 1.5% of change in the load may ready to make the combined generator. This may constitute to the power system network as would be represented in the system. So due to which the loss on the system may be reduced, and the coefficient of increasing the system response may be to the level of next case. As delta Pg of S is extended with one of the transfer function Kg by 1 plus Stg, then this may be connecting to the blocks of delta Pv of S. When this block is considering as a reference section, and that reference block is connected here, so this block may be represented by Kg by 1 plus Stg, the same control block, but it is considered with 1 by R ratio. This 1 by R ratio is treating as a delta omega of S by delta F of S, due to which it can take the return feedback path. Because of this return feedback path only, the system response may hikes to the extended level. So due to which the automatic generating control action can improve the response of the system. So these are the parameters we need to consider to maintain the automatic generator control action into the system. So here all the individual blocks will be connecting to represent the complete automatic load frequency control. This can maintain the reference signal, and that is connected to the governor block. So here governor block will develop a transfer function as a kg by 1 plus stg function. This governor block is coupled by turbine system, and this also develop one of the transfer function in terms of kt by 1 plus STT case. So this turbine is given connected as delta PM of S to one of the controller as delta P naught of S. So this system is connecting to the major power system block, as finally it is reaching to the one of the transfer function 1 by 2 HS plus D case. So this block is the response block. This response is connecting as a feedback path, and it will be treated as 1 by R. So this feedback loop position is again connecting to the reference section. Why? Because any errors that may be expressed here in this section can be given as a written path to the input section, that is excitation case. So that will be ready to make the drop over of the system, and that control action will be done at the reference point. Again, it is taking number of times as feedback path, due to which the response of the system can be maintained suitably. So this is the takeover about the system parameters. So these are some of the references which I have make over for AGC concept. So we can refer so many blocks to this system with advanced control strategies, and which will can ready to nullify the system errors into the whole entire power system network. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.